All right, let me begin with a word of prayer. Heavenly Father, we thank you for this day, thank you for the weekend, and I just pray you'd help us today just to understand a little bit more about bases. Lord, in your name I pray. Amen. All right, so let me get straight to it. Get rid of this nonsense. All right, so I am going to try to talk to you today about the concept of coordinates. In a vector space. From a pure linear algebra perspective, what I'm doing here is not the most awesome path, because in practice, in principle and concept, perhaps I should take today to talk to you about theorems about linear independence and spanning in the abstract vector space, and then after having done that, go to this topic. But I think that I'm going to turn those things around, and I don't think it's going to, I think you're going to be fine with the way we do things. Okay, so definition. If a vector space V over the field of scalars F has basis beta, and so this basis is going to be V1, V2, ... Vn. All right? So what does it mean that this is a basis for the vector space? What does that presuppose? Two things, right? One, beta is linearly independent, and two, it spans, right? So the span over the field of scalars F of beta is the whole vector space V. So it's a linearly independent spanning set for the vector space V. All right? So suppose you got all that. Then X in V has coordinate vector X sub beta equal to, let's say, C1, C2, ... Cn, if and only if X is equal to C1, V1 plus C2, V2 plus ... plus Cn, Vn. So the coordinates of a vector are the coefficients that are needed, all right, to form that given vector as a linear combination of the vectors in the basis. Example 1. If beta equals E11, E12, E21, E22, then beta a subset, and in here I mean, sorry, I really, just to be clear, I should say this is a subset of R 2 by 2, okay? Then beta is linearly independent, and the span of beta is what? It's all 2 by 2 vectors, right? So this is the usual basis, all right, for R 2 by 2. This is the standard lexicographically ordered basis for R 2 by 2. And so what I mean by lexicographically ordered is like we'd all do sort of the first number is like the first letter, so you put all of those first. This is kind of like AA, AB, And then the second one would be kind of like BA, BB. These in some sense are in alphabetical order. If you use A equals 1, B equals 2, C equals 3 code. This is the lexicographic ordering. All right, great. Then what if you got A equal to ABCD? Well, that's equal to A times E11 plus B times E12 plus C times E21 plus D times E22, right? Where those are those matrices that have 1 in one spot and 0 in the others, right? Like here, I'll just pick on this one. What's E21 equal to? That's 0, 0, 1, 0, etc. Yeah? And so, okay, great. I have this, I'm building A from this linear combination of the matrix units. So what's the coordinate vector of A? The coordinate vector of A with respect to the beta basis is equal to, what do you tell me? Oh, A, B, C, D? Yeah. So here A is playing the role that X did in my definition. Okay? Any questions? No? Example 2. Beta equal to E1, E2, dot, 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 En is standard basis. For Fn. And if we have x equals to x1, x2, dot, 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 xn, of course we can rewrite that as what? x1 times E1 plus x2 times E2 plus xn times En, which shows what? What's the coordinate vector of x with respect to beta? X1, x2, xn, which is also known as x, yes. So let me write that in words. A vector in Fn is its own coordinate vector with respect to the standard basis. So this is kind of, well, this is why we didn't need the concept of a coordinate vector up till this point, right? Because we just worked with vectors themselves, right? So this concept was kind of not needed because we were using the standard basis to write everything, essentially. But once you start using a non-standard basis, then the question becomes interesting, right? So like example 3. So let me do something that's not just a definition, that's got like a little bit more numerics to it. We could look at beta equals to, I don't know, 7, 1, and 6, 0. This would be a subset of R2, right? And then I could say, okay, so if, if x equals to, let's say, a comma b, then find the coordinate vectors of x, coordinate vector of x with respect to this beta basis, right? How would you do that? What does that mean? What are we trying to find? Can I write it out? Let's, I'll stick with my definition and call this C1, C2 for the purpose of our calculation here. So we're trying to find what? We're trying to calculate C1 and C2 such that C1 times the vector 7, 1 plus C2 times the vector 6, 0 reproduces AB, right? That's what coordinate vector of x with respect to the beta basis means. It means that I've got C1 times 7, 1 and C2 times 0, 6 to build back my vector AB. So what is that problem? Can you rewrite this? Yeah, it is a spanning question, but this is also just the problem 7, 6, 1, 0 times the column vector C1, C2, right? So can we solve that equation? I mean, we can solve this, right? Multiply by the 2 by 2 inverse. So 7, 6, 1, 0 inverse times AB. What's that equal to, though? Let's crunch the numbers here. What's the determinant? Minus 6, right? So I have minus 1, 6. Flip the diagonals. 0, 7. Put minuses on the off diagonals. That's our classical formula for the inverse in the 2 by 2 case. We get that. And what we got? Looks like we've got minus 1/6 times minus 6b, and then minus a plus 7b, which I will rewrite as b, comma, a over 6 minus 7b over 6. Right? Now we can check our work. If we did this right, what should we be able to see? Well, that is true, but that's not where I was going. So how about b times what? B times 7, 1 plus, oh, listen to me, b. Oh yeah, C1 is B, right? This is C1. This is my C2. So C1 times 7, 1 plus, what was it? A minus 7B over 6 times, what was my second vector, 6, 0? Does that equal AB? I'm just going to take a step back away from the board to see if I can see it. I forgot to bring my glasses. Mistake. So look, I get a 7b here. I get 6, that 6 cancels that 6, right? And I get a minus 7b here. So the 7b's cancel, just leave me a for the first component. This gives me a b. That gives me nothing. I get a comma b. There you go. It works. Those are indeed the C1 and C2 to make this so. So in short, we have shown the coordinate vector for this arbitrary AB vector is, as I said, b, comma, a minus 7b over 6. And there you go. So you'd ask me about doing problem 60. This is problem 60. Right. With different numbers, but. So beta, let's talk about some language here. This is a non-standard basis for R2. All right, non-standard basis for R2. And as you can see, the coordinate vector of a vector is not just the vector itself, right? It's something quite different. Just to, let me see if I can illustrate this. So application, if we look at the coordinate vector of, say, let's say, I don't know, 6, 6. So the coordinate vector of that with respect to beta is what? 6 comma what? What's 6 minus 42? Divided by 6? Minus 6, all right. So this is, of course, 6, 6. And so what I'm saying is you take 6 copies of 7, 1. Oh, I think I may need a bigger board. What does 6 copies of 7, 1 look like graphically on my scale? I mean, I'm saying 6, 6 is 6 times 7, 1, right? Minus 6 times, what was it? 6, 0. So here's my 6, 6 vector. So 6 times 7, 1. 7, 1 looks something like, it's like up 7, over 7, up 1, right? So it's like something like this, right? That's roughly 7, 1. But I'm doing 6 of those. 1, 2, 3, 4, 5, 6. And then I need minus 6 of 6, 0, which is horizontal displacement of minus 36 back from whence I came. Right? So like 1, 2, 3, 4, 5. I can't do math. Well,
you have 7 blue ones.
Oh, well, that explains it. Let's try that. Well, let's see here. But anyway, this is the thing, is if you have 2 non-collinear vectors, you can always take a number scalar, enough of one and the other to get back to the original vector. And how many of those you need are the coordinates. All right. Okay, well, there's another way to look at this we'll talk about later, but that's enough for now here in terms of the geometry. So what if this wasn't R2? What if instead of R2 we were looking at, say, Rn? And I give you a non-standard basis for Rn, and I said calculate the coordinates with respect to a non-standard basis for Rn. How would that go? Suppose beta is, v1, v2, vn, a subset of Rn, okay? And you want to calculate the coordinates of x with respect to, this, right? Then what you do is you'd be looking to solve c1v1 plus c2v2 plus cnvn equal to x. But you can repackage this, just like we did in the 2x2 example, as v1, v2, vn times the coordinate vector c1, c2, cn equal to x. And what we're really looking at there, let me just introduce some notation for this case. And I should emphasize this notation is special to the fact that we're working with Rn, okay? But since we are, this is straight up the matrix of beta. It is the matrix formed by taking the column vectors and just putting them column by column by column by column by column, making the column matrix. And of course the C1, C2, that's the coordinate vector of x, right? And okay, so we've derived a general formula. which is that to calculate the coordinates with respect to the non-standard basis beta for Rn, we just multiply by the inverse matrix to the, the basis matrix times the vector. Now, is that the smartest calculation to do? Absolutely. I think it depends on what you're after. If after 3, you want to do it that way? This is a spanning question, right? So if x is a given specific numerical vector, and you have specific vectors v1 through vn, I think probably you want to make the augmented coefficient matrix and row reduce to find the coordinate vector as the last column, right? Because this is, after all, a system of linear equations, right? So you can solve it using our previous methods, but theoretically, it's also this. Okay, we kept it real long enough. Example 5. Don't haha me yet. I haven't. You may now say haha. V equals C, let's say C2, all right? So what's this look like? X1 plus IY1, comma X2 plus IY2, such that X1, X2, Y1, Y2 are real numbers. Of course, that's a kind of complicated way to write it. You could just say Z1, Z2, such that what? Z1 and Z2 are complex numbers, right? That would be C2, complex, two-dimensional complex vectors. But what I want to talk about is this is over F equals to R. All right, so what's a basis for complex 2 space as a real vector space of dimension 4? See, if I look at this, let me call this thing, I don't know, I need a name for this thing. Let's call it Z. If you look at it, we can write Z as what? X1 times 1, 0, plus Y1 times I0, plus X2 times 1, 0, oh, excuse me, 0, 1, right? Plus Y2 times 0i. So this suggests to me that beta equal to 1, 0, I0, 0, 1, 0i is basis for complex 2 space as a real vector space. Because the span, the real span of those four vectors gives me all of C2, and it's linearly independent with respect to the real numbers. This beta, is this linearly independent with respect to complex numbers? If we allow complex scalars, is beta linearly independent? Let me rewrite beta. We're looking at E1, IE1, E2, IE2. Is this linearly independent over the complex numbers, this set? It is not, right? Because the second and the fourth are scalar multiples by I of the first and the third. It's manifestly dependent. And yet, over the reals, it's linearly independent because we can't multiply by I. That's not a real multiple, right? So, like I warned you guys, complex versus real vector space structure is different. even though beta is linearly dependent over the complexes, right? So where over the reals, yes, but the real, just because the scalars are real doesn't mean everything in the vector space is real. It just means we're only allowed to multiply by real scalars. But the original place where it's coming from is C2, which allows for complex numbers for the x component, for the first component and the second component are complex numbers. So like, now, all right, getting to my point, what's the coordinate vector of z? What's z beta? With my z here. Right. Now so this is one pretty typical choice of basis for complex 2 space, but another choice, let's say gamma, you could let gamma be E1, E2, IE1, IE2. This is another choice of basis, all right? And if you did that, what would if you look at z equal to x plus IY, where x is equal to x1, x2, and y is equal to y1, y2, right? In other words, I'm saying you take the complex 2 vector and you can break it into its real part, x, and its imaginary part, y. If you use that basis, then what happens? So all I've done is just rearranged the terms in star, right? I did nothing more than rearrange the terms in the other decomposition, right? I just took this and reordered these. It's the same things in different order. But what's the coordinate vector with respect to gamma here for z? Right. In other words, you could look at it as the real part of z, comma, the imaginary part of z. If we define this to be the real part of z, and this is the imaginary part of z for z, which is given. And sometimes you like that choice of coordinates for the complex, like complex n space, because it's just nice to have the coordinates strung out like that. Okay? Yeah, these are the two main choices.
So is beta or gamma, are they technically not sets then? Because the order matters, the set wouldn't be equal. Those two sets aren't equal.
Yeah, a basis is an ordered set. So to be fussy, it's not really a set. You could say it's a list. And truth be told, when we talk about sets in here, we're actually talking about multi-sets. You might wonder what's a multi-set. So basically, the thing is, when we look at, something like E1, E2 union with E1, E2 later, if you have been a good student of set theory up to this point, you would tell me that the union of those two sets is E1, E2. But the way we think of it in here is not that. We think of it as E1, comma, we think of it as like E1, comma, E2, comma, E1, comma, E2. Sometimes we allow reordering, but we allow duplicates. This is important to just for the sort of bookkeeping of questions about linear independence and dependence, because when I take two sets with like one with 5 vectors and another with 5 vectors, I put them together, I don't want to entertain the question, oh, how many vectors do I really have? I'm just going to say I have 10 vectors. I don't want to worry about, is there an overlap between my two sets of 5? That's just not part of our thinking. Admittedly, that means we're using multi-sets. And if not for your question, none of you would have noticed. probably. Okay, but anyway, that's kind of hard to pick up on in the questions that we have thus far addressed in here. All right, so let me talk about how to find a basis for, Oop, can I erase? So bases for column, row, and null space of matrix. So in the context of a matrix, an m by n matrix over a field, we have especially nice theorems about how to construct bases. All right. So I'll proceed by example. Let's let A equal to 1, 1, 1, 1, 0, 2, 2, 2, and finally 1, 3, 3, 3. Let's find the basis for the row, the column, and the null space of A. All right, so here's what I'll do. If we do row reduction on this, what do we got? You're like, you're actually doing a row reduction in class. How quaint. I thought you weren't ever going to calculate anything again. I did. Hey, I did something earlier. I did a 2 by 2 inverse. Didn't take that away from me. Let's see here. Row 3 minus row 2 and row 1 minus 1/2 row 2. And if you don't mind, I will retroactively do a row 2 over 2, if you'll allow me. Okay. So there you go. That's the reduced row echelon form of A. What does this tell me? It tells me a basis, for one thing, for the column space. So basis for column space of A given by pivot columns of A. Not the reduced row echelon form of A. Those will always be E1, E2, E3, which may or may not be relevant. But here, so the basis for column space of A, I would use 1, 0, 1 and 1, 2, 3. Okay, how do I know that that's a basis? First of all, as we discussed before, pivot columns are linearly independent by the CCP. What else? They span all other columns, again, by the CCP, by the column correspondence property. I can build columns 3 and 4. Well, I mean, it's kind of like, okay. I don't know. Do you really need row? I don't know if you really need to do the calculation to see the answer here, but I'm going through the motions because if the matrix is more complicated, these calculations would actually be necessary to see your way past the original matrices, original matrix various idiosyncrasies. I can't say that word. All right. The unique characteristics which make that matrix that matrix. Okay. Next up, basis for row space. Given by pivot rows of the reduced row echelon form of A, or REFA. Now, you can't really see it in this problem, like it's coincidental but true that you could also use row 1 and 2 of the matrix in this case for a basis for the row space, but there are other examples where row swaps would get you into trouble. Okay, so anyway, so following my own advice, basis for the row space of A, I can use 1, 0, 0, 0, and 0, 1, 1, 1. I do hope you're reading the notes. There's much more the notes has to offer past what I'm showing you in class here, right? Okay, how about null space? What's the null space? This is x in this case R4. I'm keeping it real. You may laugh. AX equal to 0, or don't. It's x in R4 such that AX equal to 0. Now this I cannot read straight up off the matrix, okay? Like I have to think through this. And what I have to think about is what my reduced echelon form of A tells me, right? So we have x equals to x1, x2, x3, x4 with what? What is this? What is this in the RF of A shows what? X1 equal to, oh, looks like 0, right? X2 equal to, looks like minus x3 minus x4, right? So this looks like 0, minus x3 minus x4, x3 and x4. So this is how we find the null space basis. We put in the equations, which, parameterize the solution set. All right? And what's going to happen is you're going to be able to factor out the parameters, and it's going to leave you with vectors. And those vectors are going to be linearly independent. That is just an inevitability of the row reduction process. Because if there was a dependence between these vectors, it would suggest that there was a dependence between the non-pivotal variables, which is impossible, because the non-pivot variables are free. Free indeed. Let's see here, 0, minus 1, 0, 1. And those vectors that you have there, those are a basis for the null space of A. Okay? In some sense, this is how you do problem 63. 63? I don't know. So basis for the null space. Zero, minus 1, 1, 0, comma, 0, minus 1, 0, 1. There you go. That's my standard no bells and whistles way to find these. Let's look at another example of this because it's kind of an important example. Did I say example 1? Seems wrong. This is example 7, right? 6? I missed example 6 then? Okay, example 6 then. Like you sir are an idiot. Okay, fine. How about this? 0, a 0, a 0, a 0, a 0, 1, 1, 1, 1, 1. There. This is a silly matrix. Let's find its column and row space and null space basis. So do we need to do calculation? I don't think we should. But, okay, fine, row swap. 1, 1, 1, 1, 1. Behold. Anyway, you should be able to see that the column space of A is the span of what? Span of 0, 1, right?
Yeah.
Row space of A is the span of, and you see, I mean, this is kind of silly, but you see what I'm saying? In the reduced row echelon form, the pivot row is the top row, right? I do not use the pivot row of A. That's not what you need to build the basis for the row space. You need the pivot row of the reduced. See, because the process of row reduction will flip rows around and so forth. Anyway, so it's this. And then the null space of A, well, that's where it's interesting. If X is in the null space of A, then we have that X1 is equal to minus X2, minus X3, minus X4, minus X5, right? Which means we can write X as equal to minus X2, minus X3, minus X4, minus X5. And then you got yourself an X2, an X3, an X4, an X5. Those are the free parameters in the solution set to the homogeneous problem here. And then, just like the last one, we can factor out our non-pivot variables. X2, minus 1, 1, 0, 0, 0, plus X3 times minus 1, 0, 1, 0, 0, plus X4 times minus 1, 0, 0, 1, 0, plus X5 times minus 1, 0, 0, 0, 1. It gives me no joy to write these vectors again, so let me give them names. W1, a W2, a W3, a W4. So beta equal to W1, W2, W3, and W4 is basis for the null space of A. So if you think about it, we were solving equations like AX plus B. I mean, AX equals to B before, right? The null space is as big as the solution set in some sense, right? Like, remember we've had parameters in our solution set. There's an obvious connection between that solution set problem, solving AX equals to B, and now doing this null space basis calculation. But now we're looking for a basis sometimes. So, okay. So, let's do a slightly less standard calculation. So let's find basis for W equal to f of x in, let's say, P3 of R, such that f of 3 equals to f of 2 equals to 0. All right. Then adjoin vectors from the monomial basis, 1x, x squared, x cubed, such that beta union with, let's say those vectors are called S. Beta union S is basis for P3. All right, so I kind of already spilled the beans and showed you the trick to understand this vector space. So if f of x is in W, then by the factor theorem, what do we have? We have an x minus 3 and an x minus 2 factor because they take a 0, because the polynomials are given to have zeros at 2 and 3. But then we're working with a cubic, right, which means by process of elimination, what's left is something like mx plus b, right? So it's a linear factor that's left over. And so we can rewrite that as like m times x minus 3 times x minus 2 plus b times x minus 3 times x minus 2. All right? Which maybe it's a good idea to actually multiply that out. What do we got? X cubed minus 5x squared plus 6x plus b times x squared minus 5x plus 6. So these are linearly independent, right? Why are those linearly independent? In other words, I'm claiming beta x cubed minus 5x squared plus 6x x squared minus 5x plus 6 is basis for W. That's clear. How do I know that those are linearly independent? That set is linearly independent. I think it's clear that the second one is not a multiple of the first, or vice versa. Right. Now you're like, well, x times the second one gives me the first, so isn't that a multiple? Can we multiply by x? Is x a scalar? It is not, so that does not count. It has to be a scalar multiple. VW, linearly independent, if and only if V is not equal to KW for some K in the field. That is clear for this. All right, so great. So you guys tell me, what can I make, to get a basis for what can I adjoin here? What can I put here and here in order to get a basis for P3? See, this is where a theorem called the plus-minus theorem comes in really handy. The plus-minus theorem. If g of x is not in the span of beta, then beta unioned with g of x is linearly independent. I mean, here, I already know beta is linearly independent, so if I union a vector outside the span, I get a larger linearly independent set. This is one aspect of the plus-minus theorem. So all I have to do is find something outside of W. How do you do that? How about 1? Is 1 outside W? Actually, I think you can't go wrong here, because if you think about these 4 polynomials, I don't think there's a single one of these which has both f of 2 and f of 3 being 0. The constant polynomial 1, does it have f of, you plug in 3, it's still 1. Right? So it doesn't satisfy the condition. 1 is not in W. The polynomial x, not in W. Polynomial x squared, not in W. Polynomial x cubed, not in W. You can choose any 2, as long as you don't pick the same one to complete to a basis for P3. So here, 1 and x, there you go. That is a linearly independent subset of P3, which will span P3. Now, how do I know that? I'm using theorems that I haven't really shared with you yet, and we'll talk about those next time. So this